Still here, eh? All right, let's do some really painful thermo and see what we can do with a acid-base reaction. 1.6 moles of, okay, so we have barium hydroxide, which is a base because it has hydroxide ions in it, and it's mixed with hydrochloric acid, and neutralization occurs, and so this is dissolved in water, and this is also dissolved in water, and when you pour them together, the water is going to warm up. That's energy is released when the acid and base fight. So that's our situation, and they start off with just some stoichiometry. How much base would we have needed to neutralize our acid? So let's get a reaction down here. They say barium hydroxide reacts with hydrochloric acid. This will be a double replacement, so we'll get barium chloride. And hydrogen hydroxide, also known as water. But I'm going to write it as HOH because that makes this just a smidge easier to balance, I think. One barium, that's fine. Two hydroxides means we need a 2 here, but a 2 there means we also have 2 H's, so now we need a 2 here. And that 2 means we have 2 chlorines. Oh, that's fine. Okay, so here's our balanced reaction, and they've told us a bunch of things about the reactants. They said our barium hydroxide concentration is 1.60 moles per liter. We have 200 milliliters, which I'm going to write as 0.2 liters as the volume of our acid. Concentration of the acid is 1. And we want to know what's the volume of the barium hydroxide. Well, we can get number of moles for HCl. That's easy enough. And N equals CV. 1 times 0.2 is 0.2 moles of HCl. Now, if this reaction were all 1 to 1, we'd have 0.2 moles of everything. But it's 1 to 2, meaning however much HCl there is, we only have half that much barium hydroxide. So if we have 0.2 moles of HCl, we only have 0.1 moles of barium hydroxide. 1 to 2 ratio means you either divide by 2 to get here, or you multiply by 1 over 2. Either way, you get an amount that's half as big. Now that we have that, the volume in any solution is number of moles divided by concentration. So it's 0.1 divided by 1.6, which I cannot do in my head. Maybe I could have 0.0625 liters is the volume of our base. Are we good to go to 3 sig? Yeah, everything in here is 3 sig digs so far. I know I wrote 0.2, but 0.200 would have been more accurate. So 3 significant digits is fine, and 0.0625 liters works for the volume. Now, the reason that's important is it tells us that when we mix these two solutions, we put 0.0625 liters of liquid in the same test tube or cup as 0.2 liters of liquid. So our total volume, our total solution volume is 0.2625 liters, which means our mass is 0.2625 kilograms. A liter of water has a mass of 1 kilogram. So if you've got volume in liters, you can just convert that to mass in kilograms as long as you're talking about water or something that's pretty water-like. 25 kilograms. Now, most solutions are not exactly water. Their specific heat's a little different, their density's a little different, but we can almost always fudge it and say that use the water numbers and do okay. That works for coffee and tea and Coke and almost all of our acid-based solutions. And if it's ever something significantly different, then we'll let you know. But in general, you can trust that a liter is a kilogram or a milliliter is a gram, and our specific heat will be 4.19. So we have this much water that's heated up, and it heated up by 20 up to 31 is an 11 degree difference. So our delta T is 11 degrees Celsius, and the specific heat is the usual, the pretend it's water amount, kilojoules per kilogram degrees Celsius. As soon as I wrote kilograms here, I pretty much locked myself into using kilojoules and kilograms for my specific heat. So the energy that this liquid soaked up would come from MC delta T times 4.19 times 11 degrees, and I get 12.0986 kilojoules. And you say, hang on, why are you talking about the water? They asked about the energy released by that reaction up there that you balanced and then abandoned. Those amounts have to be the same. This is like a thing where if there's a transaction at a store and I spend $16 on nachos, you could look at the amount in the cash register and say the business just made $16, and you automatically know I spent 16 getting the nachos. Those amounts have to match because it's the same money, just it's a loss for me and a gain for the company. This energy was a loss for the acid and base species, but it's a gain for the water, so you can calculate it either way. In this case, we say, I saw the water warm up, I know how much energy it must have gained, 12 kilojoules. Now I can look at the reaction and say, I know you just gave up 12 kilojoules of heat because I saw it in the water. And speaking of that, they say, what is the heat of neutralization for barium hydroxide? Well, we know that in this reaction, we just got 12.0986 kilojoules. That's our total amount. 12.0986 kilojoules. Our number of moles for barium hydroxide, conveniently we found that up here, it's 0.1. 0.1 moles of BaOH2 times the delta H we want to find. Divide both sides by 0.1 and we get the heat of neutralization is 120.986 kilojoules per mole. If we're being good about sig digs, it's 3, isn't it? Yeah, everything up there is 3. So we should trim this down to 3 significant digits, which would give us 121 kilojoules per mole. In the book, they make a really big deal about putting subscripts on these delta H's, and I think they put an N here for neutralization, perhaps, to distinguish it from other reactions. They do that like it's a big standard system that you should know, and I don't think that it is. If you want to put an N there to remind yourself what the reaction is, go ahead. I'm just going to stick with delta H and try not to clutter this up too badly. If they ask about the heat of neutralization for hydrochloric acid, we can do the same calculation we just did with the same formula we just used, but one thing's going to be different. Do you see what it is? Our total energy is still 12.098. But our number of moles, now they're talking about hydrochloric acid, so now we need the moles of hydrochloric acid. Don't use the 0.1. Under hydrochloric, we have 0.2 moles. So here we put 0.2 moles times our new delta H. And if you divide that by 0.2, you come up with 12.0986 divided by 0.2 60.493 if I follow this. Kilojoules per mole. Now, something I often encourage you to do that I kind of forgot to do here, when you write kilojoules per mole, say what you're talking about. Moles of, in this case, it's barium hydroxide. In this case, it's hydrochloric acid. That's extra important when you have two delta H's that are both for neutralization, and the only difference between them is what species you're talking about. If you write both of these as kilojoules per mole, you are asking for trouble, so please don't do that. I notice again, this comes out to 60.49, and when I was doing the key, oh no, that's okay. If you take this to 3 sigdigs, you do get 60.5. So with the corrected significant digits, this would be 60.5 and all as well. So be good about it, be better than I was here, and when you write kilojoules per mole, anytime you write moles, try to specify moles of the thing you're talking about. Otherwise, you put these two numbers side by side and you have an accident waiting to happen. Enough? You try to remember that, and I will too. See you in the next one.